Hello, my little mathematicians. Today, we are going to review equivalent ratios, how to solve them using tables, how to solve them using unit rate, and also how to compare them. So first off, for example 1, it says, Philip was asked to use 3 ounces of nuts to every 4 ounces of raisins. He used 2 ounces of nuts to every 3 ounces of raisins. Complete the 2 tables to determine if he used the correct amount. Because sometimes you double or triple or cut in half recipes. So you need to know, did I do it correctly? So what we're going to compare is we're going to compare what the actual recipe called for and what he actually did and see if he did it correctly or not using equivalent ratios. So first off, let's focus on the actual recipe. So the actual recipe is right here in this first sentence. It says he was asked to use 3 ounces of nuts, right, for every 4 ounces of raisins. That was according to the recipe. So let's go ahead and complete the table for what the recipe called for. For the top row, I'm always going to have 3 times something. And for the bottom row, to find out this part, I'm always going to have 4 times something, right? And whatever you choose to multiply by, you have to do the same thing to the top and bottom in order to create equivalent ratios. Well, what did you multiply 3 by to get 6? You multiplied by 2. So do the same thing down here. 8 times 2 is 8. Now 6/8 is equivalent to 3/4 because they both reduced to 3/4. And I multiplied both the top and bottom by the same thing, and I kept the initial ratio the same. Okay, so now going from there, double check if this was correct. 3 times what is 9? 3. 4 times what is 12? 3. Yes, they both were multiplied by 3, so it's correct. Okay, 4 times what is 16? 4. So multiply the top by 4. And 3 times 4 is 12. So this is my completed table for what the recipe asked for. Now there's what he actually did. It says he used 2 ounces of nuts. Okay, so that went with the nuts. And he also used 3 ounces of raisins. Okay, so 3 went with the raisins. Now, just like before, I want to keep this ratio consistent. So 2 times something on the top and 3 times something always on the bottom. Okay, well, since they gave me this one, 3 times what is 6? 2. So 2 times 2 is 4. 2 times what is 6? 3. So 3 times 3 is 9. And then double check that this was correct. 2 times what is 8? 4. So this should be multiplied by 4 as well. And 3 times 4, yes, is indeed 12. I know that technically you didn't have to do this one, but it's just good to double check that the pattern was consistent to make sure that you used the correct pattern. Now that I have my 2 tables complete, I can use it to answer the question, did he use the correct amount? So what I can do is I can search for maybe the raisins and see, okay, did he ever use 4 here? No. Did he ever use 8 here? No. Did he ever use 12 for raisins? Yes, right there. So when he used 12 raisins, he should use 9 ounces of nuts. Well, when he used 12 ounces of raisins, he used 8 ounces of nuts. So he didn't do it correctly, right? So if you find the same matching number for one of your values, compare it to your other value, so for nuts, and then see if those top numbers match. Since 8 and 9 didn't match when you used 12 for the amount of raisins, I knew that those 2 ratios aren't equivalent. So no, they are not equivalent because the recipe calls for 9 ounces of nuts for every 12 ounces of raisins. But when he used 12 ounces of raisins, he only used 8 ounces of nuts. Now, this is one way to solve this problem, is to create equivalent ratios and then fill it out and do it in the way that we just did. But another thing you could do is you could reduce both ratios and then see if they reduce to the same thing. Well, 3/4, what it called for, is fully reduced. 2/3 the amount he used, is already fully reduced. Is 2/3 equal to 3/4? No. Okay, this amount cannot reduce to that amount. They can't become each other. So that's another way that we could have also determined that those amounts aren't equivalent. I didn't necessarily have to do an equivalency table, but sometimes they ask you to complete a table. So we reviewed that as well. And that also makes more sense to some people. But whichever way makes more sense to you, that's the way you can solve. Now, the next thing they ask you to do in this unit is to compare ratios. Remember, fractions are just a fancy word for ratios, right? When I'm asked to compare them, there's two ways that I can solve. The first way is the way that I prefer. Change them both to decimals. Now, in this particular section, we're allowed to use calculators. So when you're asked to change it to a decimal, remember, all you do is you take the top and divide it by the bottom. That's what a fraction bar actually means. It means this divided by that. So type that into your calculator. 2 divided by 4. What do you get? You get 0.5. And that makes sense. 2/4 reduces to 1/2, and we know that 1/2 is like 50% or 0.5. Okay, the other one they want is 5/6. So type into your calculator 5 divided by 6. And you'll see it's 0.8, 3, 3, 3, 3, 3, 3, 3, 3, 3. It keeps going and going. So instead of writing all those 3's out, I'm just going to put a line above the 3 to indicate that the 3 keeps going. Now, the important part before I actually compare these of what's bigger is I need to have the same number of numbers after the decimal. Since this has 2 numbers after the decimal, I need to have this have 2 numbers after the decimal as well. What's bigger, 0.83 or 0.50? 0.83 is bigger. So the great big end, or the alligator mouth, is facing the 0.83. So according to that, 0.83 is representing 5/6. So the great big open end, or the greater than part, is facing the 5/6. Now, I did say that there's 2 ways that we could solve this, right? Well, the second way that we could solve this is by getting a common denominator. If you get a common denominator, then you can just compare the numerators. Okay, so we're going to put an or here, because either way you do it is correct. It's just a matter of preference. I prefer this way, especially if you're allowed to use a calculator. Top divided by bottom. There you go. Type it in. You get this decimal compared to this decimal. But if they're really hard numbers and you're not allowed a calculator for that section, maybe you want to compare them by getting a common denominator. So I have 2/4 versus 5/6, right? Well, what can both 4 and 6 become? Look at the bigger number 6. Can 4 become 6? No. 6 times 2 is 12. Can 4 become 12? Yes, it can. So both 4 and 6 can become 12. By the way, another way to find a common denominator is to do the LCM. That's what the LCM is. It's what can both of those numbers multiply to become. All right, now that I found a common denominator, I can figure out the numerator that would make this fraction equivalent to this one and this fraction equivalent to this one. Well, 4 times what is 12? 3. Whatever you do to the bottom, do to the top. 2 times 3 is 6. So 6/12 is equivalent to 2/4 because they'll both reduce to 1/2. Right here, this one, 6 times what is 12? 2. So 5 times 2 is 10. 10/12 is equivalent to 5/6 because they both reduce to 5/6 in simplest form. Now that I have the same denominator, I can just compare the numerators. What's bigger, a 10 or a 6? The 10 is, so 10/12 is bigger than 6/12. So I'm going to have it facing this way, which matched what we did before, right? So it's just a matter of preference of which way you think is the best. Now, there's one thing I do want to point out, though. Let's add in a bonus right here. Let's call this number 2b and bonus number 2c. Let's say I want to compare 0.9, and then they put a little circle in the middle to like write a greater than or equal to sign, and 0.83. And then this one, they wanted you to compare 0.3 versus 0.3 repeating. The trap is that you look at this one and you're like, oh, 0.83 is obviously bigger than 0.9. Like 83 is bigger than 9. So clearly this is bigger. And this is why it's important to always make sure you have the same number of numbers after the decimal. Because here's 2 numbers after the decimal. Let's let this have 2 numbers after the decimal. So add a 0 as a placement holder. Now what's bigger, 90 or 83? Ooh, 90 is actually bigger. So I would have gotten it wrong if I didn't put that 0 placement holder there and I just went like, oh, 0.83 is bigger than 0.9. Because remember, you look in the tens place right here, 8 versus 9, 9 is bigger. Okay, but it's easier if you just write the same number of numbers after the decimal. This one, if in the tens place you go to compare them, they're the same number. Well, what's the next number that would come after that? Well, here, the next number that comes is another 3 because it's 0.3 repeating. This one, it's not repeating, so there's nothing there. Let's put a 0 placement holder. So what's bigger, 0.30 or 0.33? 0.33 is bigger. So the trap here would be to think that they were equal when you first started, because you're like 0.3 and 0.3 repeating. Oh, they're both 0.3. Yes, but this one's only 0.3, or you could think of it as 0.30 versus this one's 0.33333. It keeps going. So the next number would be another 3. Just something to keep in mind when you're asked to compare, and if you choose the route of going with comparing by using a decimal, always make sure that you have the same number of numbers after the decimal when you go to compare. Let's move on to example 3. And remember, if you ever want to try some of them, you're always welcome to pause the video, try it yourself, and then unpause it and come back to check yourself. For example 3, it says Mark runs 5 miles in 40 minutes. If he continues at the same rate, can he run 14 miles in 120 minutes? Try to answer this question by using equivalent ratios. When you're solving using equivalent ratios, it doesn't really matter what you choose to go on top versus on the bottom, as long as you're consistent. Okay, so let's say you go 5 miles in 40 minutes. Okay, then how far can he go in 120 minutes? Well, let's see. 40 times what is 120? 3. So do 5 times 3 on top, and you get 15 miles. So according to my equivalent ratio, he can go 15 miles in 120 minutes. Well, they're only asking if he can run 14 miles in 120 minutes. So yes, he can. He can do 14 plus 1 more. Okay? So yes, he can run 14 miles in 120 minutes. Because he'll actually have already ran 15 miles. Oops. All right. Now, another way that we could solve these, I prefer doing equivalent ratios because I don't have to think as hard about what goes on top versus what goes on the bottom. But some people, it was confusing of, well, should I choose to do the 14 here? But 5 times nothing is 14. So that's why we chose to do this one. And they're like, I don't like it. Okay, well, then you can choose to do the unit rate. So what I do for the unit rate is you just have to think to yourself, it matters what goes on the bottom, right? Because for unit rate, the denominator is going to become 1. So how you decide what to put in the denominator is they said, can he run 14 miles in 120 minutes? So let's get the denominator to become miles to become 1. So then I can just multiply it by 14 and see how long it'll take. All right. So if he goes 40 minutes, it takes him to do 5 miles. Okay, well, I want to solve using the unit rate, so I'm going to divide by this denominator of 5. Well, 40 divided by 5 is 8. And 5 divided by 5 is 1. So you have 1 mile. Now that you have a unit rate, a denominator of 1, I can multiply that by 14. So this is how long it takes him to go 1 mile. How long does it take him to go 14 miles? So let's multiply this by 14, and I get 14 miles. And how long does that take? Well, 8 times 14 is 112 minutes. So does he have enough time to run 14 minutes if he only has 120 minutes? Yes, he does. He has 8 minutes to spare, right? So yes, he can run 14 miles in 120 minutes, okay? Because it'll only take him 112 minutes to run 14 miles. Now, had I done this the other way, had I done miles over minutes, 5 miles in 40 minutes. This is why I don't necessarily like the unit rate, because it's a little bit more trickier. Okay, so I would divide by 40 this time. And then you're like, 5 divided by 40 is an eighth. That's weird, right? And if, for those of you that were typing that into your calculator, okay, if you typed that into your calculator, 5 divided by 40, you get 0.125. So he can go 0.125 miles, and 40 divided by 40 is 1 minute. And since I got minutes to become 1, I'm going to multiply by, well, how far can he run in 120 minutes? Well, 1 times 120 is 120 minutes. And 0.125 times 120 is 15 miles. So he can run 15 miles in 120 minutes. So the question was asking, can he run 14 miles in 120 minutes? Yes, he can, because he can not only run 14, but he can run 14 plus 1 more. So you can see that there's more than one way to get the answer. It's just a matter of preference of what makes the most sense to you. If you like the unit rate route, okay, well then you just need to, whatever you got the denominator to become 1 of, since we got miles to become 1, then I would multiply them both by 14 miles and then look at that to answer my question. If I got my denominator to become 1 that was minutes, then I'd multiply it by 120, because for 1 minute, I went this distance. Well, how far could I go in 120 minutes? All right. Or if that's just too much thinking, you could always just fall back on the equivalent ratio route. All right. And that is how you use equivalent ratios or finding unit rate to answer questions. Congratulations on mastering yet another standard.